Starting again with the caveat that I'm not really a physicist, definitely not a nuclear physicist, but fusion is of great interest to me as a climate scientist because this could really change the game in terms of decarbonizing, and also because I already have a couple of podcasts and this one fits nicely into it, especially this infographic that I got from Visual Capitalist. And I want to also make a couple of points from a Washington Post article on what are the future challenges in actually translating this big news about successful ignition into working functional nuclear fusion reactors and so on. We already made some of those points, but we'll just go through here what comes up in terms of costs and so on. The science of fusion ignition, a major scientific breakthrough in nuclear energy. This is from Living Capitalist, Visual Capitalist, as you'll see at the end, the tagline. So what happens in a typical nuclear fusion reaction? You have fuel like deuterium and tritium, which we already talked about as the ones that fuse at lower temperature and produce a lower temperature plasma than, let's say, boron and other fission material, which can actually produce energy in a better way. As we already saw, this one tends to produce neutrons. So intense heat and pressure force nuclei together, and the fused nuclei produce an extremely unstable form of helium, and unstable form of helium then becomes regular helium by getting rid of a neutron. So the nucleus stabilizes into a standard form of helium, releasing the energy and a neutron. And we talked about how this neutron is not a conducting particle, so we have to extract that energy by containing it and letting it bombard a container, which heats up, and then we use the heat to, for example, warm water and produce steam and drive turbines. But we said the neutrons colliding with the container then begins to make the temperature of the container high and produce radioactive activity, which is not a good thing. So US scientists, as we saw already at the National Ignition Facility, part of the Lawrence Livermore National Laboratory, have produced a specific nuclear reaction that may transform the way we generate and use energy. This is the hope. This is why I'm interested in it as a climate scientist. Here we describe nuclear fusion and illustrate how this discovery may pave the future for clean and sustainable forms of energy. Just to revisit some of the basics, what is nuclear fusion? Nuclear fusion is the combination of atomic nuclei to form a heavier nucleus. We said this is what happens in stars. Our sun is fusing hydrogen to produce helium and giving us the energy we have survived on. Releasing large amounts of energy, it is commonly performed with isotopes of hydrogen called tritium and deuterium. I think you already know isotopes, what isotopes are. Hydrogen has one proton, one electron, whereas deuterium has one proton, one neutron, and one electron. Tritium has two neutrons. So the proton atomic number is what makes it a hydrogen, but you have isotopes. They can be stable or unstable, as we know. Isotopes in general. Small amounts of hydrogen fuel produce enormous amounts of energy. 1 cup could theoretically power a house for hundreds of years. This is always exciting to hear, but how we get there is still not that obvious. Nuclear fusion is clean energy. It does not produce harmful atmospheric emissions and only small amounts of short-lived radioactive waste. Nuclear fission, as we know, which is the most is used now extensively across the planet. Well, not as extensively as some would like, because nuclear fission is also considered a clean energy, renewable energy. Of course, it involves mining, getting rid of radioactive waste, the security issues and general political inaccessibility that people are scared of it, and so on. Germany, for example, started getting out of nuclear fission after the Fukushima accident in Japan, and Japan itself has phased out many nuclear plants and now wants to go back, but this is not so easy, and so on and so forth. The same process powers the sun and other stars. Scientists have been trying to replicate it on Earth for almost 70 years. You always hear about China producing an artificial sun, which is essentially the same kind of experiments. Adding to the details of what we already looked at in the last podcast on ignition, what is fusion ignition? Fusion ignition is the term for a fusion reaction that produces more energy than it takes to create it. This is very critical to become self-sustained. Additional energy inputs are not needed after the ignition, and the reaction becomes self-sustained while supplying large amounts of energy by fusing the material that's there in this hot plasma. This is necessary in order for nuclear fusion to become a reliable energy source. Up until now, scientists were only able to break it even, in the sense they put some energy and they did not generate more energy. And the biggest news about the ignition at the National Ignition Facility in the US is that they put some amount of energy and they got more energy than they put in, and there was a cascade of fusion reactions. So looking at that detail here, how did NIF achieve ignition? The National Ignition Facility uses a special setup called inertial confinement fusion that involves bombarding a tiny pellet of hydrogen plasma with lasers. We illustrate this process below. So we talked about trying to control the plasma with magnetic fields, with solenoidal circulation stability ideas, and the so-called inertial confinement, where we said if we increase the density to a large enough level, then the plasma, which is an ionized gas which can fly away and lose the energy, can be kept for small amounts of time, confined enough to drive further nuclear fusion reactions. Very short, but as I said, if you want further details on how to stabilize plasma in fusion reactors, you can look up more details elsewhere. Okay, so here is the setup. So you have a contraption that is a diagnostic instrument manipulator and is used to positioning and diagnostics. So it's holding this little thing here, which is a capsule. So parts of the fusion chamber in this cross section here, a golden barrel called Hohlraum, Hohlraum. Hohlraum. I don't know how it's pronounced exactly. You can look it up. So that holds a capsule pellet containing deuterium and neutrium layer of fuel. They are put as frozen molecules, or let's say clusters, about the size of a peppercorn. So this golden cylinder is what gets bombarded by the lasers. The process of nuclear ignition itself, lasers are fired into the Hohlraum, figure out how it's pronounced. 192 laser beams fire into both ends of the Hohlraum, creating a super hot plasma that heats up its golden walls. In the second step, the heated walls of the Hohlraum produce X-rays which blast towards the capsule pellet and erode its surface. In the third step, the capsule pellet implodes rapidly, kickstarting fusion. So you need high temperatures and pressures to make this fusion happen. If the heat spreads fast enough, the energy coming out can outpace the input, i.e. the ignition. So they put in 2.05 megajoules, as we saw before in the previous podcast, and they measured with this diagnostic contraption that they got out 3.15 megajoules coming out, which is 54% more energy that was put in, which can then drive cascades of fusion reactions and become self-sustained. Although this study produced a small yield, scientists successfully proved that this long-sought reaction is possible to achieve. Now, scientists will need to perfect and optimize the reaction components in order to upscale the yield and figure out how to commercialize fusion technology to the masses. The process is estimated to take several decades before several decades fewer than originally expected. So we have accelerated the process, and the idea again is that so many private players and public funding is going in, that this will be like the vaccine, accelerated development of COVID vaccines, which shorten the time scale of decades or decade and longer that takes for vaccines in general to about a year. And of course we are still trying to see how effective they were and what exactly they accomplished, and what the long-term effects are. And what China is going through now in terms of COVID could be related to the fact that the Chinese vaccines may not have worked as well as expected. So this is from elements.visualcapitalist.com, which always puts out nice infographics which I have used elsewhere. Coming to what the Washington Post article that just appeared today in the paper, I'm just trying to look up the date, 20th December 2022. I didn't put the link in here, sorry. There's more than one way to do it. So this article is about the cost and the challenges of how to go from the ignition success to actually having functional fusion reactors that will either feed to the grid or serve energy needs in other way off the grid, for example. There's more than one way to do it, so that's the ignition. Scientists are trying to replicate the scientific reactions that happen inside the sun to create nuclear fusion power on Earth. To power those experiments, the major difference comes in what type of reactors researchers use. One type is called the inertial confinement, which is what NIF used, which relies mostly on lasers. It was used by Lawrence Livermore National Laboratory, which announced last week's achievement, which we looked at already. The other is magnetic confinement, which uses magnetic fields. A few researchers are using a hybrid of the two. We talked about high temperature magnets, which are better in terms of being able to be cooled by liquid nitrogen, which is easier than the regular magnetic fields, which need cooling with liquid helium, which is much more difficult because helium can leak out in all sorts of ways and hard to confine. Secondly, the scientific and engineering challenges lie ahead. Federal researchers shot high-powered lasers at a tiny capsule to achieve net energy in a reaction lasting a few billionths of a second. Okay, researchers can do that only a few times per day at most, but if that type of solution were to be used broadly, lasers would need to fire at least once per second, maybe up to 10 times per second, and this will include lots of challenges in terms of cooling the system of lasers and so on. Thirdly, it'll cost a lot. To capitalize on last week's announcement, scholars, trade association experts, and venture capitalists said the government and private sector must dedicate a lot more cash to make nuclear fusion a realistic solution. Nearly $5 billion has been invested in the industry. Trade association data shows, with about $2.8 billion coming in the past year. We already looked at this in the last podcast. Much of that has come from the private sector. The government, mostly through the Energy Department's Fusion Energy Sciences program, is spending about $700 million a year to fund the science. Okay. The fuel matters. Many researchers use a fuel source composed of deuterium and tritium, variants of hydrogen, isotopes of hydrogen. Deuterium is found in seawater and is abundant, so this is always critical. Tritium produced naturally is extremely rare and in a potential shortage. Already this is a big challenge. Companies would have to find a way to source it in mass, probably getting it from nuclear reactors, which create it as a byproduct. So that brings up the whole question of how to produce it and still be carbon neutral, etc., how to transport it, and how to safely transport it and use it in the fusion reactors. It's a long way to reality. This is the sobering message from all quarters after the ignition success. Americans should not expect their toasters, cars, or laptops to be powered by fusion energy anytime soon, scientists said. Even if everything goes according to plan, The first test facilities that demonstrate nuclear fusion as a viable power source for towns and cities, so utility scale, may not be online until the 2030s. Even if it happens by the 2030s, it's fantastic news in terms of bending the curve of CO2 and greenhouse gas emissions and decarbonizing especially the energy industry, and then cascades into getting away from the carbon trap. From there, scientists and experts said building out full-scale facilities could take another decade or so. This is a race. 2 degrees centigrade, 1.5 degrees centigrade global warming targets by 2100, and how we get to net zero well before that, and so on. Okay, of course there are lots of other issues to worry about in the end. Technology transfer to poorer countries, whether people can afford them on their own, or whether rich countries will again continue to dominate this energy source, and what it means, etc., etc. But without worrying about all that, let's just get very optimistic about what has been accomplished in terms of the ignition success and the huge amount of investment that's going on into actually making them sustainable in terms of fusion reactions. Okay.